Our next speaker is Dr. Qasim Mehmood. Dr. Mehmood got his BS degree in 2008 in electrical engineering from International Islamic University in Islamabad. He got his PhD in electrical and computer engineering from National University of Singapore. Currently, he is an assistant professor of electrical engineering in information technology, University Lahore, Pakistan. He's in the beginning of his career, but has already published more than 30 papers and has been getting very heavily cited. So, he is one of those rising stars. I'm happy to invite him to tell about his recent work on engineered plate nanodevices for optical biosensing or bioimaging.
Oh, hello. I'm audible.
Just a little. I guess you are. It's a little lower, but we can hear you.
Okay. Thank you. Your nice introduction. My name is Qasim. I'm working as an assistant professor at Information Technology University, and I am leading a research group named as Nanotech Lab here at ITU. So today, before going for the talk, I would like to acknowledge the few funding agencies and institutes which are helping us in experiments and fabrication. Engineered flat nanodevices for optical bioimaging and sensing. So to be honest, my work is mostly towards the experimental realization of individual devices instead of the systems. But since the theme of this symposium conference is more towards biophysics, so I try to show few applications of those the individual devices in bioimaging and biosensing. So before starting my talk, I would like to briefly introduce my research group. So we have our own web page. So if you are interested, please feel free to visit, and we can get connected via email or any of other resources. We also have a Facebook page where we keep posting day to day the updates and openings, etc. So over here at our lab, we focus on several interesting research areas that include photonics and metamaterials. We are also specialized in microwave and antenna engineering and applied computational electromagnetics and few other interesting areas mentioned over here. So we are working together with other around 5 to 6 faculty members, including myself, Dr. Zubair, Dr. Kashif, Dr. Usman, and Dr. Tosif, who are focusing on different yet connected areas of electromagnetic sensing, etc. So in our total strength is around 5 to 6 faculty members, and we have currently 11 full-time PhD students working under our supervision, with more than 30 master's students, which include full-time and part-time. And apart from that, we have around 10 research associates working on different areas. So since we established our group in 2016, we were able to tap on the top venues, including advanced materials, and light science applications, functional materials, etc. And we are currently collaborating with national and international institutes, including NUS, IMRI, Singapore, PostTech, and LUMS. So, introduction, I would start from optical constants. As we know that optical constant have two parts, refractive index and extinction coefficient. So refractive index actually controls the velocity, that is phase of the wave. I'm talking about electromagnetic wave, whereas extinction coefficient is responsible for absorption. So it depends what kind of application we are looking at. If we are looking for a transmission based optics, then definitely we would like to have as minimum as possible extinction coefficient for that spectral range. And if we are talking about absorption and dichroism, etc., then we would be interested to have more this extinction coefficient phenomena. So if we look at the expression for electric field, so it is quite evident that refractive index over here is basically responsible for controlling the phase of this electromagnetic wave, whereas this exponential factor results in the decaying of this particular electromagnetic wave. So there are three fundamental characteristics of the wave that includes amplitude, phase, and polarization. So later we will see how we tailor these three fundamental characteristics of the light or electromagnetic wave using artificially engineered materials. So in bulk optics, generally, mostly we use these glass and these bulky components like lenses, prisms, wave plates, etc. All of them are actually made up of glass, and they use propagation effect, means phase and amplitude and polarization are actually controlled by the physical parameters of the component, optical component. So as we know that all of these components are bulky, big in size. So if we come towards the system, definitely the, let's say microscopy or spectroscopy, anything consisting of such optical components will be bulky, larger in size. So how about compactness? So if we want to go for miniaturization, so obviously we need an alternative to conventional optical components that are obviously easy to fabricate, highly efficient, and possesses a smaller footprint. We need a planar components which are compact, lightweight, and that can essentially be integratable with photonic ICs. So back in 2011, the idea of meta surface was introduced by Professor Capasso from Harvard. So what he proposed that by using, generally if we talk about Fermat's principle, so going from one medium to another medium, we accumulate a phase, light is bent towards or away from the normal, depending upon how the things goes. So over here, we do not, there is no phase change at the interface. So what was the idea by Professor Capasso's group, that by putting an array of such geometries of nanoresonators, array of such nanoresonators, we can actually introduce an abrupt phase at an interface. And these resonators should be of sub-wavelength. So if we talk about visible light, for example, so sub-wavelength is like less than 400 nanometer thick. So if we now compare this kind of nanoresonators array, planar array, and compare the conventional optical components, so it can actually significantly reduce the size of these optical components. So this novel idea led to the demonstration of several interesting applications, demonstrations, including meta lenses, holography, etc. So what exactly is metamaterial? So meta means beyond, and materials, conventional materials. So metamaterials are artificially engineered materials. So they could be like three-dimensional, planar, flat. It's a general, more big, broader term. So it can give some properties which are mostly impossible to achieve to a naturally occurring materials. So since surface comes from a planar or flat thing, so meta surface would be a surface which can give some properties which are essentially impossible to achieve through a surface of naturally occurring materials. So these kind of nanoresonators, planar subwavelength dimensioned nanoresonators, array of these nanoresonators is called as metasurfaces. So just to give you a comparison, for example, in natural materials, we have atoms. So in metamaterials, metasurfaces, we have artificially engineered subwavelength featured atoms, and we call them meta atoms. So over the years, this whole thing, and there is a comparison of a size between conventional objective lens and the one meta objective lens in terms of a size. So size is about 10 raised to power 4 times thinner for the case of meta surfaces. So the idea transformed from science to technology. There is a chart of publications in the initial years, and now with the passage of time, it is going more towards the patents and more towards the application-oriented research. So I would now briefly explain about metasurfaces for bioimaging and biosensing. So recently, after these initial demonstrations, now people are exploring metasurface empowered bioimaging and biosensing tools, which can give lightweight and compact solutions for bioimaging and biosensing. So in this regard, there are several demonstrations, experimental lab grade demonstrations, prototype demonstrations have been reported by several groups that include endoscopic optical tomography, chiral imaging, fluorescence imaging, MRI super resolution imaging, and also biosensing of enantiomers, DNAs, etc. So at first I would explain the enantiomer detection. So a chiral compound consists of enantiomers, which are actually enantiomer and its mirror image. So mirror image means it cannot be superimposed. Both of them cannot be superimposed to each other. So generally in drugs, single enantiomer drugs are more efficient rather than a mixture of both. So standard way of identifying these single enantiomer drugs or chiral sensing is to use circular dichroism spectroscopy. But the thing is, standard chiral molecules possesses extremely small circular dichroism. So if I look at this bottom figure, ABC, so for example, there are two different chiral solutions, different. So if we see there is a LCP and RCP, so there is a very slight difference on the transmission side between LCP and RCP transmission. So if we talk about circular dichroism, so intrinsic circular dichroism in a chiral molecule is extremely small. So similarly in figure B, again, there is another solution, and still you see the difference between the two polarizations is very small. So what if we use metasurfaces or metamaterials, and on those metamaterials we pour in the chiral liquid, chiral molecules. So now you can see it can give a extremely high circular dichroism. So which means the sensing ability is enhanced to a greater extent. So that was in 2017 when they have given the Fabrizio and the other co-authors presented this kind of metasurfaces, bilayer metasurface, twisted metasurfaces. So they can actually get a very high circular dichroism, and they have shown the experimental results for chiral sensing as well. So now I would briefly talk about chiral imaging. So chiral imaging based on light polarization is also a topic of interest for particularly for biological community. So it generally in the conventional setups, it relies on sequence of several bulky optical components. So generally an optical system or imaging system, the basic ingredient or base fundamental unit is lens. So if we talk about objective lens, a sequence of lenses, so meta surfaces give us a freedom of designing meta lenses which are significantly, drastically smaller compared to conventional lenses, and that can ensure compact systems for chiral imaging, etc. So for designing a meta lens, so because it's an array of meta items, so at first we have to decide the meta atom, and then we have to, because if we talk about lens, so it is nothing but phase accumulation. So we need to arrange these meta atoms in an array that would be a planar array of meta atoms, and in order to, and each meta atom should definitely give a different phase in order to get a constructive or destructive interference, whatever we want to have. So the first step is to identify the meta atom, the fundamental unit. So now it also depends upon whether you want to have a polarization sensitive or polarization insensitive imaging. So the second step would be to optimize these meta atoms to achieve a complete 2 pi phase control. And then in order to design a lens, you have to arrange these meta atoms to acquire a desired lens. And once you have the lens, that will be the overall results, focusing performance of such meta lens. So as I have mentioned, this is what we use in our group, two fundamental units. So one is nanobar as a half-wave plate, and the second one is nanoindex waveguides. So as the geometry suggests, it's quite evident that these half-wave plates, and their name also suggests, they are polarization sensitive. So they act as a half-wave plates. So so there's one chat. Maybe I present and then look into that. Okay, so over here, they are polarization sensitive, and in these nano half-wave plates, we achieve a different phase by rotating these half-wave plates. However, in the nano index waveguides, we change the diameters to achieve a different phases. So over here, now I have given a simulation results for a unit cell, and you can see by rotating these half-wave plates, we can bend the wavefronts of the light, incident light, in a desired way. Similarly, for the nano-index waveguides, by changing the diameters of these waveguides, we can acquire the desired wavefront bending. So once we have decided the meta atom, then it's about the matter of arrangement of these meta atoms if for the desired phase mask, what kind of phase masks we want to have. So from this was again from Capasso's group. They have presented chiral imaging, and the idea was to use two half-wave plates. One is green and another one is blue. One focuses LCP and another focuses RCP at different transversal points. This was their experimental setup, and they have in a single field of view, they have imaged this beetle. So under LCP light and under RCP light, we can clearly see the different features of this beetle skeleton. So then in 2018, there was our Bobby's group, those who have presented two-photon microscopy using dual wavelength meta lensing. They have replaced the objective lens with the designed meta lenses, and here is the performance of their lenses. We can see that both the wavelengths are actually both the wavelengths are focused at the single focal spot, and there was the comparison of their results under their dual wavelength meta lens and conventional objective lens. Both of them actually their lens gave a very good imaging performance. Then it was again from Professor Capasso's group. They have used these meta lensing for nano-optic endoscopy. Conventionally, this single mode fiber, and there are grain grade index gradient index lenses are being used for the focusing of the signal or a ball lens. However, these conventional methods, these conventional lens suffer from aberrations, astigmatism. So what they have introduced to use a meta lens to realize a diffraction limited focusing for, and they call it nano optic endoscope. So this is how they can focus this object onto this image plane using meta lens, and their performance is it's quite evident on the right side, second column, that their focusing performance is far better in comparison to ball lens and green lens. And they have further took the OCT images through their setup, and they have shown the comparison with ball lens and green lens, and it is quite obvious that their lens gave a far superior performance in comparison to the ball lens and green lens. So now I would briefly introduce what we do at ITU, or what we have done in ITU, few of highlighted works. Back in 2015, we have presented, so the meta surfaces story was like this. The initial demonstrations were based upon plasmonic meta surfaces, because gold fabrication was much easier, and it was difficult to find a suitable dielectric material to achieve a high performance. So initial demonstrations were on plasmonic metal surfaces, and this was our presented work on multi-focusing meta lens. The lens was able to generate 3 different focal spots, and it can also give a dual imaging. For example, for LCP, if we give the LCP light, this is on the transmission side, and these are the virtual images. So as linearly polarized light have both LCP and RCP, so 3 spots used to appear. But once we use a LCP, then we used to have a central spot, and then if we use a RCP, we used to have the other 2 spots instead of all 3. Then we have also presented these hexicon, or we're going to meta hexicons. So meta hexicons gives a very clear advantage on conventional hexicons. One is definitely in terms of a compactness. Then another bigger issue is for a conventional hexicons, that if you want to realize a higher order hexicons like 2, 3, 4 order, then it is not possible to achieve this with a conventional hexicon, because you will require an external spiral phase plate. So our concept was to integrate this spiral phase plate and lens into a single on-chip hexicon, and we call it meta hexicon. On the same footstep, we have also used the vortex lens. So in brief, we can structure light in a desired way, uh, and we have proposed the concept of integrating multiple bulk optical components into a single on-chip component. And these are after plasmonic metasurfaces, we have also given a few demonstrations on hydrogenated amorphous silicon-based devices, and these characterizations actually were done in LUMS in Dr. Savi's group. So apart from meta lensing, vortex lenses, we have demonstrated several different devices, unique devices for holography, meta holography. Holography is lensless photography, in which we encode the phase mask, and then we shine the light, and then we can retrieve the desired phase mask. So these kind of meta surfaces are known as computer generated holograms. So this was our first demonstrations in holography in 2019, where we have integrated 2 different holograms for 2 different helicities. So once we impinge the left circularly polarized, we used to achieve a ITU, and for the RCP, we used to get the RHO. RHO is a professor role from Postec, so that was in collaboration with his group. So all the work was done over here. We get the fabrication from them. These were the optical setups and then measured results under LCP, RCP, and linear polarization and elliptical polarization. So it's quite obvious if we are using LCP, we get only ITU and RCP, RHO, but if we use linearly polarized light or elliptically polarized light, both the image appears simultaneously. Then we have also demonstrated directional multiplexed hologram, and the work was published in Nanoscale Horizon back in 2020. In that case, we have integrated again phase profiles, but this time we have integrated the direction. So if we impinge from one side, we get one sort of phase mask, and if we impinge on the other side, we get another image. And this was work was also selected for the cover page for this Nanoscale Horizon. Okay, both of these works were, there was one issue that we could not use the white light because they were only for the one wavelength. So then there was a point, and there was another issue that it requires the polarized light. So we wanted to have a broadband, unpolarized kind of thing. So then we came up a new design methodology in which we can actually design a meta surface for unpolarized light, and it can also work under the broadband from blue to red light. So these were the results for this one, and this was the schematic image. We made a crescent star, encoded this image, and we impinged the white light, and we used to get image performance. And these were for a broadband analysis where we have impinged different lasers and captured their imaging profiles. Apart from these holograms, we have also able to achieve this asymmetric transmission, circular dichroism. I have mentioned one of them over here. And there are more works can also be found from my profile or from our website. So to conclude, I have introduced my own research and introduction to motivation and potential of meta surfaces for bioimaging and sensing platforms. And what we have done at ITU, as I have mentioned in the beginning, that our work is mainly towards new methodology, individual devices, but due to obviously limitations of equipment, facilities, we cannot go for these systems. So I personally feel that we have a very good group of students and faculty members over here at ITU, and this forum could be a nice way to collaborate. Few of people who can, with whom we can work together to realize some interesting systems, some interesting applications. So thank you very much.
Okay, so
I hope I'm on time, right?
yes, you are. Thank you so much for a nice presentation. We have plenty of time for questions. The first one is coming from Dr. Shahid Khan. Please go ahead.
Hello, Qasim. Yeah, so that's quite interesting. I mean, I personally do not know this area at all. There are a couple of points. One is I'm not clear your work at ITU. So if I'm understanding correctly, you're not making the materials, or do you actually make the materials?
No, for fabrications, we depend upon post-tech
You import
foreign
them.
collaborators. Yes.
Okay, so you import them. So
yes,
then,
yes.
you at ITU, then do you design? You've mentioned design.
Yes, design, optimization.
All right. Okay. Yeah.
Physics.
But yeah. No. I think it would help me and possibly others if you would tell us a bit more about what design actually entails. So you've got the material. Then what do you do? Do you go and sit on a computer and you make a computer model to predict, okay, if you arrange the metamaterials or the meta atoms, as you say, in a particular way, this is the kind of hologram you get. And then do you then once that material is made elsewhere or whatever, then you test your theory. Is that what design means? What does
Yes,
design mean?
yes, exactly. You are right. You are right. This is what
Well,
we
no,
do.
I mean, you tell me, go through step by step exactly what you do.
Oh, okay. So
Yeah.
initially we check with our collaborators. So what kind of materials they can make. So we
Okay.
get the optical constants from them, and
Okay.
then we look at the let's say, for example, some holography, or let's say broadband optical holography. So then we
So,
first
so you,
this.
but you must have some idea at what you're looking for, right?
Yes,
I
yes,
mean, so,
exactly.
so
So
I mean, presumably, so you get the material and then you identify some problem that you feel could be of interest, or do you have a theoretical question? Uh,
yes, I mean, it could be the new idea, it could be new design methodology. I mean, it could be potential application. I mean, not at the system level, potential optical component. And then keeping that thing in mind, we select the appropriate geometry, and then we have to optimize to get the required phase. And then
but no, no,
we have,
but just hold on. I mean, I'm lost. I mean, you're going too fast for me.
oh, okay,
Uh,
sorry.
so, uh, so if there's a potential application, say you've identified a potential application, then how do you select the appropriate geometry? How do you do that?
Yes, for example, as I mentioned earlier, for example, if we are looking for something for the white light,
Yeah, all right. So
and
let's
it's,
take that as an example. All right. Yeah,
yes,
good.
yes, yes, unpolarized light, white light. So we need to look at, let's say, two things. One, that we need a material which is transparent. For example, if we are talking about transmission holography, it should be transparent from 400 to 700 nanometer.
Yes.
And then the geometric response, if we impinge the light, it should be polarization insensitive. If we are talking about white light, it should be unpolarized, right? So then after
Okay,
material,
but suppose it is not polarization sensitive, then what?
then we have to find a new way of realizing that thing.
Okay,
We
so
have to look
then
at
you
the
go back to your collaborator and then you have them.
not
Uh,
collaborator, then it's on us then how to get the appropriate geometry, how to get the theoretical modeling that this
okay,
kind of
so
geometries.
then you do all right. So that's what I was
Yeah,
looking for. Okay, so
yes,
then
this
you
is
do theoretical modeling to see
calculations,
what.
optimization,
Fine.
simulations. Yes,
Okay, that's what I wanted to know. Okay, so that's what you do largely.
yes, this, and then
Okay.
characterization, this also we do. I mean, once fabricated,
Characterization of the. So how do you
fine.
characterize a material then?
I mean, once the device is there, then we have the lasers,
Then you
mirrors,
do test
condense.
to see whether it, but it's
Yes,
largely modeling. I think.
yes. Vinay.
All right.
Characterization is
Okay.
no. I mean,
Great. Okay. So all right. Fine.
yes.
Okay. Good. Thank you.
Thank
No,
you.
that kind of clarifies a lot.
The second question is from Atta. Atta, go ahead.
Qasim, very nice talk. Is it very important कि जो what's the incident light direction is? Has it always to be normal for these meta optical components to work,
Not
or
necessary.
it is flexible in its operation? Yeah.
Okay, because right now it's more about research and prototype.
Mm.
So,
Mm.
if we put it at some angle, so
Mm.
alignment is very difficult. So the
Mm.
total fabricated device is generally 200 by 200 micron. So then just to, I mean, keeping in mind the characterization facilities we have, we prefer to have it normalized. But the groups which can do it in a very nice way, they have facilities. It's no restriction that it should be normal. It could be at any instant. Now people even made it like, motorized laser, so where they can actually rotate from one angle to another, and they can do the angle multiplexed, let's say holograms, imaging, this kind of thing. But for us, I mean, we do not have enough freedom to do that kind of experiments. So that's why we limit.
Okay, so how far away we are from, let's say, meta surface-based microscopes commercially available, for example?
Oh, wow. Now the biggest, to be honest, issue is the fabrication challenge, because if we look at the dimensions, they are like 300 nanometer or something like this, the meta atom size. So you see, if we want to have a microscopy, we need a lens of a very large size, like 1 cm, something like this in the XY dimension. So generally they use EBL, electron beam lithography. So it is more like the individual meta atom is very small, and in order to make a complete device, you need like millions of these meta atoms. So now the bottleneck is on the fabrication side. They cannot fabricate a very big device. But now this technology is kind of, they are coming up with new fabrication methods where they can fabricate a larger device. And then I think there will be a point, it's not that far. People have done, have demonstrated few new fabrication techniques where they can fabricate the larger devices. But still, I mean, I think it will take few years before it will be like commercially in the system.
Okay, there maybe they can switch to patterning techniques to get rid of the E-beam lithography.
Then I think maybe the problem is the resolution of that individual meta atom. That restricts the smallest feature size is the problem. You have to maintain that size. So that is right now the debate, how to look for a new fabrication techniques.
Okay. Last question from Dr. Shahid Khan.
Yeah, so yeah, I think to get to the nitty gritty, it's all fine to talk about microscopes, but what we need to know, it would really help me to know exactly what microfabrication is being done in Pakistan. Is any microfabrication of the kind you've talked about being done in Pakistan? And if so, where?
I don't think that this kind of
nanofabrication.
Right.
So that's the first question. So I think we can forget about microscopes and things like that. The first thing we have to decide is, how do you get any kind of microfabrication started in Pakistan?
No, Shahid, may I jump in a bit?
Yes.
Qasim have been fabricating some of his component at LUMS, I think, as far as I know.
Well, but I've just asked him. He said that there's nothing. So all
no,
right.
I
So
mean,
can we get a clear answer to this?
I think we have tried quite a few times, but the thing is, we always come short of with few steps.
Okay.
Complete device fabrication is always a problem. So that's why.
Okay, great. Well, no, I think this is important, because I think one of the issues for this workshop is to pin down exactly where we are in terms of our capabilities, so then we can define step one. So as far as I understand it from this talk and from what Qasim is saying, making a microscope is not step one. It's probably step, I don't know what it is, but it's definitely not step one. Yeah.
Then also, I think fabrication requires lots of money. I mean, financial resources.
Yeah, I mean, there are a number. Well, I mean, so this is one of the things. Maybe Qasim, we could discuss this in the roundtable. This would be a good thing to take up, and then we can see how we can maybe contribute and help people like you on this.
Thank you so much.